introduce our speaker today. Thank you all again for coming, and great to see everyone virtually. My name is John Sutherland. I'm very pleased to welcome our guest speaker today, Professor Michael Hauschild, who is from the Technical University of Denmark. The acronym is DTU when you convert to Danish. Michael's a good friend, and he has been teaching at the university for about 25 years. Michael has his master's degree in chemical engineering and then his PhD in terrestrial ecotoxicology, both from DTU. He's been very involved in CTAC and has been involved for many years in lifecycle assessments of products and systems. And I know him through the International Academy of Production Engineering, CIRP. And with that brief introduction, let me introduce our speaker today, Michael Hauschild.
Thank you, John. Thank you for having me, and welcome all. As John said, I've been in this field for many years. I'm leading at the Technical University a group of researchers. We're around 25 people, including PhD students, who are working on quantitative sustainability assessment. And as you can see from the bottom of the slide, this is also the name of this research team. And we have that as our core focus, really, to the methodologies, the methods to put numbers on sustainability, to assess sustainability. And we've been working on life cycle assessment. I've personally been working on that since I finished my PhD, actually, in terrestrial ecotoxicology. And in lack of some good research money, so I could continue in the ecotoxicology, I by chance stumbled into the field of life cycle assessment, which at that point was quite new. And yeah, well, then I stayed there. So this is how things happen by chance. But we've been working on life cycle assessment for all these years, and I would say until around 10 years ago, gradually the realization dawned upon us that we in LCA we're covering. We take a relative perspective on sustainability. So we say, well, is it more sustainable this product or the other product, this way of obtaining a service or another one? Is it more sustainable to drive an electric vehicle than to drive a diesel car, and so forth? And this is fine. This is useful. Ecoefficiency, we call it. I'll come back to that. But we realize that, on a product level, things tend to just get better and better. So the new version is very often, the new version of a product is very often more sustainable than the old version. But that, if we take the grand picture, doesn't mean that we're moving in the right direction. We have huge problems with climate. We have huge problems with biodiversity loss of species caused by a multitude of different types of environmental impacts. So something is wrong. And what we realized was we need, of course, to have an absolute perspective. We cannot just do with the relative perspective that LCA offers us. And this is what this presentation is about. So first, I've called it, or you could call it also from better, which is the relative perspective, to good enough, which is the absolute perspective. When is it good enough? How good does it have to be? First, I'll just take us briefly through the sustainability challenge that we're faced with as engineers and as citizens. I'll introduce the concept of eco-efficiency and LCA as a tool to measure that, and then I'll briefly take this discussion that I already embarked a bit on now on relative and absolute sustainability, and then go into how can we define the boundaries for this absolute sustainability. If something is absolute, it means that we need to have some targets, some boundaries that we can say, if it's better than this, then it is sustainable and not just more sustainable. And then a brief discussion towards the end on how we can turn LCA into a tool for absolute sustainability assessment. What are the challenges there? So if we first talk about the sustainability challenge that faces us, I'm sure you're all familiar with the Brundtland Commission's definition of a sustainable development, the United Nations Commission on Environment and Development, which stated the sustainability or sustainable development as a development that meets the needs of present generations in a way that doesn't compromise future generations' abilities to meet their own needs. So you can say a very anthropocentric definition of sustainability. It's about meeting needs, our needs today, and the needs of those who come in the future. So where's the environment in that? Well, of course, it lies in the fact that we have to meet our needs in a way that doesn't compromise the ability to meet needs in the future as well. So that has to do with the environment. But I'd like to take a much more, what can you say, concrete view on absolute sustainability. So here you see a graph that shows the development in the temperature of the atmosphere over the last 100,000 years before today. So that's what you have on the y-axis. Oh, sorry, the x-axis is the time axis, and the y-axis is a temperature axis. So this is the temperature relative to today. Today we have the temperature reflected by the dashed line, and then the very lively curve here illustrates what was the temperature, how much lower can you see in general, how much lower was the temperature at a given point in time, 60,000 years ago, for instance, than it is today. 60,000 years ago, about 20 degrees lower than it is today. On the left side, you have the way that this has been measured. This has been measured in ice cores from Greenland or Antarctic, based on the fraction of the oxygen 18 isotope in the air bubbles that you can extract from such ice cores. It is a bit technical, but it's very strongly related to the temperature in the atmosphere at the time when the snow fell that later became to this ice and entrapped the air bubbles in it. And what you see here is, I would say, a very dynamic development. We've seen dramatic changes in temperature. We've seen over very few years, if you look at around 72 to 75,000 years ago, suddenly we see within very short time, a decade maybe, maximum a century, a temperature change of 15 degrees. So it's been a very dramatic and unstable climate until around 10,000 years ago. So the last 10,000 years, which is what is called the Holocene, the period since the last glaciation, because this is during the Ice Age, most of it. So the ice, melts away from the northern and southern extreme parts of the hemisphere around 10 to 8,000 years ago. And then we see the development of this is the period called the Holocene. And what we notice there is that the temperature temperature regime has been extremely stable. It's been warm, of course, compared to, it was the Ice Age, right? So it's been warm, but it's also been very stable. And this is the period where we see a huge explosion in the number of people on the planet. If you look above the graph, you see some events in the history of the modern human. So you see, the modern human originated by evolution. It's supposed around 250,000 years or so ago in Africa, southern parts of Africa, I believe, or central parts. And around 90,000 years ago or so, it's estimated that at least the first signs that we see of humans, modern humans out of Africa, is from that period. So they start migrating out of Africa and gradually spreading, propagating over the whole planet, arriving first in Australia. And you can say, how on the earth did they get to Australia? But you must remember that during the Ice Age, there was a lot of water bound in ice. So the average sea level has been between 100 and 200 meters lower than it is today. So there were many places you could just walk that you cannot do today. Anyway, it spreads all over the planet. And we see in the Holocene, suddenly when we're around 2,000 years into the Holocene, we see the beginning of agriculture, simply because people stopped dying. So we have, during this long Ice Age period, had very strenuous conditions for life. We have had quite few individuals, globally speaking. We're talking 10,000s, 100,000s, maybe at points at the verge of extinction, and certainly extinct locally, no doubt. But then, with a very stable climate that we have in the Holocene, we no doubt see a growth in population, which means that this hunter-gatherer lifestyle that humans have lived through the Ice Age, that this can no longer go on, because the carrying capacity of land is very low when you live as a hunter-gatherer. I mean, you hunt down the animals, you move to another area, you start hunting them down there when you know, as a protein source. But when the population density goes up, suddenly there are no animals where you're moving in because somebody was already there and killed them. So people settle down, they start agriculture, gradually developing agriculture. And we see all the great civilizations, not just European. This is a very Eurocentric slide. I have to apologize for that. I didn't draw it. I snatched it from the internet. You can see the address below. But of course, it's all human civilizations, not just in Europe, but also in America, the Americas, and also certainly in Asia and Africa. So all over, we see them as a consequence of agriculture, because agriculture simply allows us to produce a surplus that allows us to have people who don't actually do work, or just do the kind of work we're doing using our heads, but not work to produce food that, you know, you don't need to do that. So others are doing that. So you can have the development of these big civilizations. And you also see a growth in population numbers, which, well, when I was born, I think we were around 3 billion people on the planet. Today we are 7.8 billion people on the planet. And around the mid of this century, we are forecast to be close to 10 billion on the planet. So the stable climate has certainly allowed us to proliferate. Now, what's an interesting question here is, if you look at this graph, you can say, where is the anomaly here? What's the normal situation and what is the not normal situation? And I would say, looking at this, the Holocene is a very different situation, at least. Of course, we don't have the ice coverage anymore. But why is it that we have such a stable climate in the Holocene? Because that is certainly not the normal when we're looking at this graph. And I don't think anybody is able to actually answer that question. And that's a bit concerning, because if the normal situation is what we've seen over the majority of this period, and we are entering back into the normal situation, this is a dreadful thought, with 7.8 billion people on the planet instead of a few hundred thousands that can live as hunter-gatherers. So this is, of course, a very worrying perspective. And this is what led a group of researchers around the Stockholm Resilience Institute to develop the concept of planetary boundaries. What they did was and this is, you know, these are highly esteemed researchers. There's a Nobel Prize winner in there. They publish the main papers in Science and Nature. So it's not just any bunch of people, but they, you know, brainstorm what could be the processes out there that support this stable climate. And they identified 9 processes. I'm just presenting their work here now. So climate change, of course, our contamination of the atmosphere with the greenhouse gases is an obvious candidate, but also biosphere integrity, because what you see, the big difference from the Ice Age up to the Holocene is, of course, that you have ecosystems and other ecosystems, art-rich ecosystems spreading over large parts of the planet. And they speculate that there's, of course, some kind of self-regulatory mechanisms involved that stabilize the climate. And there's no doubt in their mind that ecosystems must play a role there. So biosphere integrity is important for this. And therefore, of course, also our use of land system change, freshwater use, our manipulation of biogeochemical flows, and so forth. So they identify 9 processes. And for each of them, they say, well, we can create a model for our impact inside this process, where we have a control variable around along the x-axis here that expresses or represents our pressure on the environment, the man-made pressure in the environment, and then a response variable that represents the state of the resulting state of the environment. And what you can see here, if you take the example of the climate change, the control variable that they suggest is the concentration of carbon dioxide in the atmosphere, and the response variable is then the climate response. And if you want a response variable that follows a sequence or a course like this, it could be, for instance, the coverage with sea ice of the planet over the year. What you see is, as you increase the concentration of carbon dioxide, nothing happens until you reach a certain level. There is a threshold. If you exceed that threshold, you launch some positive feedback mechanisms that dramatically change the state of the environment as represented by the response variable. So you would like to avoid passing that threshold. So you would like to know where are we relative to that threshold, and you would like to know how far can we move before we pass the threshold. The problem is we don't know exactly where the threshold is. There's an uncertainty range around it. And these authors, the Stockholm Resilience Initiative here, they define the planetary boundary as the boundary that delimits what they call a safe operating space. As long as we are below the boundary, we should be safe as concerns this process of stabilizing the Holocene situation, the climate. And the planetary boundary is put at the lower bound of the uncertainty range, so that means that the green, the end of the green area here in the cause effect figure they have. And then the yellow zone, that's where you may have passed the threshold, you may not, you don't really know. Of course, the further you move into the yellow zone, the larger is the probability that you have passed the threshold. And when you move into the red, you are quite sure that you have indeed passed the threshold. And for each of these 9 processes, or rather you can see there's some question marks here, so for some of them this is still not made operational, but for these processes, they then also go in and say, okay, so where are we? What is the current level of the control variable? And where are we in terms of the response variable? And you can see as they judge it, we are for climate change, we're in the yellow. So the threshold is probably with the way they define it, in accordance with the Paris Agreement. So that would mean, not exceeding 1.5 degrees temperature increase, stay well below 2 at least. And that's something like 450 parts per million, or maybe it's 400, or maybe it's 500. That's your range. And we're in the yellow because we're at the moment at 414 parts per million in the atmosphere or thereabout. So we're in the yellow. We may have passed it. We most likely still haven't, but actually we cannot really be sure. So it's yellow over here. And then when you're looking at the biosphere integrity, that's where it's really bad. This is measured, the genetic diversity indicator is the rate of loss of species. And it is orders of magnitude above the natural rate of loss of species. So they say we're far, far, far above the threshold for biosphere integrity. And likewise, they define these 9 processes. So let's just park that here and say, here is a measure of what environmental sustainability in absolute terms means. That means staying below the planetary boundary. Okay, let me introduce you to something else. You may be familiar with it, but then I have a calculation example that may be interesting for you. This is the iPad equation. You should notice this is a T, it's not a D, so we have nothing to do with Apple here. It is simply a way of expressing the current level of environmental impact as the product of the global population, the P, the affluence, the A, and T, the technology factor, that's the environmental intensity of our technology. So the environmental impact per created functionality of our technology. Graydon and Allenby, you have the references out here in their book, Industrial Ecology. They suggested that we measure the A, the affluence as GDP per person, gross domestic product per person. And if you take that form of the equation, then you will have your technology factor, your environmental intensity, expressed as impact per created value, because otherwise this equation is false. You can see GDP and GDP cancels out, persons and population cancel out, and then it says I equals I, which of course is correct. But why is it useful? Well, it's interesting because population and affluence and technology factor here, technological or environmental intensity of the technology, is here seen as 3 drivers of environmental impact. So what it says is, if you increase the population, all others equal, you'll have a higher impact. So more people with the same affluence and the same technology will cause a higher environmental impact. And if you increase the affluence of a given population size with the same technology, you will have a higher impact. So where are we in terms of the sustainability challenge? Well, if we look at the population, the global population is currently predicted to level off around 10 billion. Actually, it may also start declining towards the end of the century. That's the latest UN forecast I've heard. Because what happens now is that a big part of the population increase that we see is due not to high birth rates. In certain countries it is, but it's actually in big parts of the world, in Southeast Asia, it's mainly driven by longer life expectancy. So people live longer, and then of course we will be more people, even with not very high birth rates. So the global population is increasing. The affluence, the material standard of living, the GDP per person is growing strongly, has been growing strongly. I have here a graph where you can see the GDP per person. This is numbers from the World Bank, globally, global numbers, the development from 1960 up to now, 2019, in absolute numbers. And you can see the increase per decade. If you look in the second column, simply just dividing, very simple spreadsheet calculation here. So you see an increase in standard of living, and you see that it has typically been somewhere around 1.3 to 5, extreme in the 80s, but apart from that, maybe up to 1.8 factor per decade. So, and then if we're looking at the last one, the impact, it already exceeds sustainable levels, as you just saw in my slides about the planetary boundaries in many areas, in many fields, not all. Some of them we are actually well below. If we're talking ozone depletion, this is a problem that we have actually managed. Well, we still have problems with ozone holes, but this is due to what we have done in the past. This will probably repair itself. It's expected towards the middle of the century. If we're talking acidification, this was a big impact in the US, in Canada, in Europe, back in the 80s. When I was a student, this was the big environmental problem we were talking about, acid rain. It's another type of environmental problem where we've identified the sources. First, we had the political discussion. Has this got anything to do with man-made activities? Many fascinating theories about what caused the acid or the forest decline. And then eventually we agreed, okay, it is man-made emissions. It's emissions of sulfur oxides, of nitrogen oxides that cause the decline or the death back of trees, or at that time that was the issue. And then we started regulating the sources, cleaning the fumes from the power plants, getting rid of the sulfur content in the fuels, putting catalyzers in our cars, all of this stuff, and actually managed, I don't know the numbers for the US, but in Europe we have reduced the emissions of these causing substances, emission flows, by somewhere around 70%, specifically targeting the most sensitive source receptor situations. And acidification is no longer a problem in Europe, and I think in North America as well. It's a big problem in China, but they can now look at what we have done, and then they can see, okay, it's possible to do this. We know what we need to do. It's more a matter of deciding whether to do it. So it's not everywhere, but certainly for climate, certainly for biosphere integrity, and that means biodiversity and all the different environmental impacts that can affect that. We are far below. We are far above the boundary. So what is the challenge? Well, let's do some. I mean, we're engineers, or at least I am, and many of you too, I guess. Let's do some math here. So we have the iPad equation here. Let's look at the example of climate change, and let's look at 2030. I take this number because in Denmark, last year we passed a law that the Danish society must, by 2030, have reduced its impact of greenhouse gases by 70%, 70%, of the 1990 level. That's about halving what it is today. So we need to reduce by around 50% our impacts of greenhouse gases in the Danish society. This is now a law. I mean, any government in the meantime coming in has to follow this law, and it's the whole parliament was behind it. So it's interesting to look at that for us. I think also the Paris Agreement, that's basically the Paris Agreement. That's what the world needs to do if we want to follow the Paris Agreement. But what does that mean for the technology? Well, if we can solve the equation here for the technology, and we can see that the technology factor, so the environmental intensity of the technology, is the environmental impact, divided by the population times the affluence. Well, the impact, as I argued, has to be halved in 2030 compared to what it is today. So it's 0.5 times current situation, 2020 situation. The population is predicted to forecast to grow by around 10% in 2030. So we will, according to UN forecast, be around 8.7 billion, not 7.8 as we are today. So that's about a factor 10% on top of what we have today. And the affluence, well, you saw the number before. If we say 1.3 as the change that we have in 2030 compared to today, that means that the technology factor of 2030 has to be around a third of what the technology factor is today. So what does that mean? It means that the environmental intensity of the technology overall, this is not a specific technology, this is across all technologies, in 2030, the environmental intensity has to be a third of what it is today. So the technology in 2030 has to deliver what it delivers today with 35% of the climate change impact that it causes today. And this is overarching. There are some technologies that can easily do this. You know, if you decarbonize your electricity system, you can go towards zero. We're on that track in Denmark at the moment with mainly wind, but also biomass, solar. But some other areas, this is really a big challenge. Well, it's always a big challenge, I would say. So you may have heard about this factor 3, factor 10, factor 50. The point is the technology factor, the impact caused by our creation of wealth and economic value for a given target year has to decrease 3 times for 2030 for climate change. But if we're looking towards 2050, much higher factor. In the Paris Agreement, if we want to meet that, we need to be carbon neutral in 2050. That means emitting nothing. So that's in principle an infinite technology factor reduction, or it's zero, sorry. I mean, the reduction is infinite. In order to counterbalance the growth in population and material consumption, and at the same time achieve the needed reduction in environmental impact. So that means if we want to be environmentally sustainable, and we understand sustainability as staying inside the planetary boundary, not exceeding for climate change or for any other impact, the carrying or the threshold of the environment, to allow us to keep an environment that runs more or less in the way it does now, a climate system with the stability that we have known throughout the Holocene. This is the challenge. And this, I think, here is timely to introduce ecoefficiency, because ecoefficiency is what we normally operate with in engineering, in life cycle engineering. We define that as the ratio between the functional output of a process or technology or whatever we are looking at, and the environmental impacts that it causes. So that's actually just the inverted of the technology factor from before. It's a reciprocal here. So improved ecoefficiency means creating more service, functionality, output with less environmental impact. Now, lifecycle assessment is the tool. I'm not going to tell you details about lifecycle assessment at all, so I hope you're familiar with that tool. But it's the tool where we, over a life cycle of a product or a product system, we fix the delivered service. So when we're comparing two products, A and B, we ensure, or no, we're not comparing two products actually, we're comparing two different ways of obtaining a given function. And we have what we call a functional unit, which is a quantitative expression of the functionality that these two ways of obtaining it, that they give us. It has to be the same functionality. It could be to transport you from A to B, whatever, from home to work and back again, commuting every day or every work day in a year. That could be an example of a service. And that can be done by an electric vehicle. It can be done by a diesel-driven vehicle. Maybe it can be done by a car, by a bike. Maybe you can walk depending on the distance, whatever. There are different ways of doing it. And we fix the service in LCA, and then we quantify the environmental impact associated with using this way to obtain the service. So biking versus electric vehicle versus diesel car. over the whole life cycle, looking at all relevant environmental impact, climate change, but also the whole range of other relevant impacts for that technology. So this means LCA is a tool to quantify eco-efficiency. So the eco-efficiency challenge is to increase the eco-efficiency in 2030 by 3, and in 20 later by up to a factor 50 or maybe even higher improvements. Is that at all possible? Well, let's take a look at history. Here we see the example of lighting technology, the development in lighting technology over the last, well, close to 300 years, from the candle over the oil lamp, the Edison lamp, the incandescent, the compact fluorescent tube to LED lamps. What we see here is more like 3 orders of magnitude increase in, this is then energy efficiency, it's measuring lumen per watt. And you should notice this is a logarithmic scale on the y-axis. So a similar logarithmic plot. You can see it's actually an exponential development in the efficiency over this period. It's more or less a straight line here. So there's a huge potential. And this is not just lighting technology. We see this for many technologies, increasingly so. You know about Moore's law, perhaps, about the density of transistors on an integrated circuit. Doubling every 18 months or so. That's a driver of technology development. That's an exponential development that we have there. We have several examples of these in some of the basic technologies that are really the foundation of a lot of innovation. So it's not so impossible. Of course, 10 years is not a lot of time, but you know, technology can do a lot. However, there's also a development in consumption. If you look at the same example, the lighting, you see here a graph where you see along, well, you see a number of different dots here, and they are representing different locations at different points in time. And you see the relationship between the consumption of light at in that location, at that community, at that time, as a function of the ability to purchase light. So the GDP divided by the cost of light. And what you see is, this is double logarithmic. So of course, many things look quite linear in a double log plot, but still over this period, over the past 3 centuries, and even now, we spend about 0.7%, or not 0.7, 0.72% of the GDP on light, and 0.54% of the GDP on the consumption of energy associated with light. So, in spite of improvements in efficiency of lighting sources of 3 orders of magnitude over this period, we see that we spent the same amount of our same share of our ability, economic ability, on light and on energy for light, and that in spite of the fact that the GDP and the GDP per person has grown by orders of magnitude in the same period. So actually, we spent much, much more, both on light and on energy for light, than we did back 100 or 200 years ago, despite the fact that the energy or the light sources have become incredibly much more efficient. So what happened there? Well, what happened was that consumption, the affluence, and efficiency are not necessarily independent. Actually, sometimes an increase in the or reduction in T, so that's an increase in efficiency, leads to an increase in consumption. Because if the technology gets more efficient, it also gets cheaper to use, and then you use more of it. And this increase in affluence may actually neutralize the reduction in the T factor or the increase in eco-efficiency. This is known as the rebound effect, and it's not an unusual effect. We see it actually for quite a lot of different technologies. I'm sure you can think of examples. In Denmark, we've certainly seen that the impact of the person transport sector by cars has been growing and growing and growing at a time where the efficiency of the cars has been going up. So it's the same type of mechanism. We have very high car or taxes, I should say, both on fuels and also on cars in Denmark. But never so the cost of using the car means a lot for people's ability, of course, and the fuels are very expensive. But when the efficiency goes up, so does the consumption. And this is where the relative assessments kind of come to an end. So LCA supports relative assessments, same or higher functionality with less environmental impact. So we, on a scale from lower to higher impact, we are moving in the direction of lower impact. That's what the LCA can tell us. But it cannot tell us, it can tell us that the green solution is more sustainable than the blue one. But it cannot tell us whether it's sustainable, something we can sustain, a way that allows us to meet the needs of the present generations without compromising the ability of future generations to meet their own needs. Where is the boundary where it becomes unsustainable? What's sustainable in absolute terms? How can we decide that? Well, if we take the Brundtland Commission's definition, that's about fulfilling needs today and in the future. It doesn't really talk about which needs. You know, it could be the fundamental needs, food, shelter, clothes, safety, security, but it can also be higher levels of needs. Smartphones, you know, what's comprised here? How are we going to fulfill them today and not least in the future? How will future generations fulfill their needs? For how many? This is very difficult to make operational. So while the definition is conceptually, I think, strong, it is operationally extremely weak. We could take a starting point instead in the planetary boundaries, as I suggested, kind of as a top-down prescription of what is a sustainable level of impact. So if we're talking about three pillars of sustainability, the economic, the societal or social, and the environmental, you can say, well, the environmental here, seen as Earth's life support system, is then indeed a boundary of the others. We can have trade-offs between the different dimensions of sustainability, but only as long as we respect the absolute boundaries of the environmental system, because otherwise the whole thing collapses and we can forget about human needs and economies. So this brings us back to the planetary boundaries here, and then I'd like to take it over to the types of impact that we're typically operating with in LCA. This is the European reference method, the ILCD method, where we have, you know, a handful. Those of you who are familiar with LCA would know about many of these. So climate change is one, but there's a whole range of others. Like we talked about acidification here earlier. We talked about ozone depletion. There are many others. Toxics from chemicals. We have particle-borne air pollution, photochemical ozone, and so forth. And in order to make this operation in LCA, what we did was we defined for each of these impact categories a carrying capacity, defined as the maximum sustained environmental intervention that the natural system can withstand without experiencing negative changes in structure or function that are difficult or impossible to revert. That's a very, what can you say, specific definition. It's kind of a no effect level. It's akin to the critical low concept that we know from acidification. So it's similar. We have an ecosystem state, we have a human pressure, we have a carrying capacity here. Very similar to what we saw for the planetary boundaries. And we go in and we try to quantify the carrying capacity for all these impacts. And then this is typically expressed as a state. We have, in this framework here, we have drivers, man-made activities that leads to pressures on the environment, emissions, that leads to changes in the state of the environment, that leads to impacts on the function of the environment and so forth. And then we have political responses up here. But typically the carrying capacities are defined at the state level. So examples would be that it could be parts per million carbon dioxide in the atmosphere or milligrams per liter phosphorus in water, freshwater systems, where the pressures would be emission flows. So how many tons of CO2 equivalents per year, greenhouse gases are we emitting, or how many kilograms of phosphorus equivalents per year? This is what we normally do in life cycle impact assessment. We translate pressures that we have in the inventory of the life cycle assessment to changes in states. And our characterization factor is for that. Now what we need to do is we need to take them and translate the states that we get from our boundaries, the carrying capacities, back to pressures. What is the amount of CO2 equivalents or the amount of phosphorus equivalents that we can emit per year before we exceed the carrying capacity of the ecosystem? So for each of these many impact categories, we find out what is a sustainable level of impact that we need to respect here. And we express that as the permissible impact per average person. So those of you who are familiar with life cycle assessment will know that we apply their normalization references, which we typically do as personal equivalents, which are basically what is the background impact of society? How much climate change does society cause per year overall? Ozone depletion, human toxicity, cancer, and so forth. And we can express that as an impact for an average person. How many kilograms of CO2 equivalents from a person in a year? Now, what we do now is we say, how much is the permissible impact, the impact that allows us to stay below or not exceed the carrying capacity? How much is that per person per year? So we take the carrying capacity here, we take the space below the carrying capacity, and then we divide that space on the number of individuals who contribute. So if it's a local or regional impact, it's the people in that region. If it's a global impact like climate change, it's the number of people in the world. And here you have the numbers that we have arrived at for all the impact categories we address in this impact assessment method. So you see for climate change, a little less than 1 ton of CO2 equivalents per year, or maybe just a half, depending on which carrying capacity level you base it on. I can tell you that the average impact from a Dane today in Denmark is around 17 tons, 17 tons of CO2 equivalents per year. So here you have a factor 17 or 34 if you want to become sustainable, and you're a Dane. So how do we use that? Well, the normalization, this is where we take the impacts from our 2 alternatives. We've done a life cycle assessment. We've quantified what is the amount of global warming, acidification, and so forth for each of the alternatives. And then by taking this list of normalization references, we calculate the normalized impact score for alternative A, for instance, by taking the impact and divide it by the person equivalent. Then we have the number here. Now what we do is we take and replace this table of current levels of impact with a table of impact levels that respect the carrying capacity. You could call it sustainable levels. How does that come out? Let's take a look at a case study. Here we see 4 windows. It's a case study we've done. Different frames, a wooden frame, wooden aluminum, PVC, and wood composite frame. We've done a whole life cycle assessment. The whole life cycle main driver of impact is actually the heat loss in the use stage. These live for very long. You see the functional unit, a certain area, light transmittance for a certain duration, over 20 years. And the results we get are these. So this is the number of person equivalents for different environmental impacts on the x-axis here for each of the 4 alternatives that I mentioned before. And you can see it expressed in person equivalents. So over the 20 years, a wooden frame causes 5% of 1 person equivalent, so of the impact of an average person in a year through its production, use, disposal, but mainly due to the heat loss through the window frame. This was normalized against current levels of impact. If we now normalize it against sustainable levels of impact, we see a different picture. We see much higher scores for some of the impact categories because now the reference that we are dividing by, we're expressing the impact of the window relative to, is much, much smaller. As I said before, it's a factor 10 or 17 if it was a Dane, but for a global citizen, it's around a factor 10 lower for climate change. So if we just go back, we can see the shift. This was compared to normal current levels of impact. Sorry, this is normal levels of impact, current levels of impact, sorry, and this is sustainable levels of impact we compare it to. So that means that just one window over 20 years uses more or less the total climate change allowance of 1 person in a year. But you'll also notice that some of the impacts actually go down here, meaning that the reference, if you look at, for instance, acidification, you will see that the reference we're using here is higher. So acidification goes down, right? When we go to normalize against sustainable levels of impact. So how can we interpret that? If we take the consumer perspective, you can say, well, that's kind of an environmental budget that we have here. It's really how large a part of my environmental space, my allowance, is occupied by this product. Is it worth that much to me? It's a little bit like money. I mean, you have a certain amount of money you can use, and you look at a product, you'd really like to have it, but is it this much worth to you? You know, when you cannot use more than the money you have. So you can think of it as a sustainable impact budget or a personal environment, also, yeah, environmental sustainability space. Societal or company perspective, how do we do this for company? A company needs to find out, are we sustainable? How do we allocate the space between companies? Well, between societies, we can do it per capita. So we can say the US has a space which is equivalent or proportional to its number of inhabitants, just like Danes. We have all the same space on a personal level, so this translates into the countries. But there could be other ways. There's no scientifically right way. This is ethics. How do you want to do it? For a company, per created value, per generated employment, what's the use of a company? What is the service it offers to society? Why should it be allowed to take some of our space? I think that could be the rational. Per satisfied need, maybe. It meets our needs. It helps meeting our needs, food production, car production, whatever. Or according to the current space. We could also take that approach. If the world needs to shrink by 70% in 2030 compared to 1990, everything needs to shrink that much. So those who were big in 1990 are still big in 2030. They're just 70% smaller. Everything shrinks in the same proportion. That's called grandfathering. These are different principles you can apply, and there's not. I don't have a correct answer here. We've been working on testing the different approaches, see what difference they make, and of course also looking into the ethics behind them. So is it meaningful to talk about a sustainable product? Well, if you want, at least first you need to quantify what are the impacts of the product. So you do a life cycle assessment on the product, and then you can compare that, if you are an individual, to the share of your sustainable space that you want to spend on it. That's the consumer perspective. If you're a company, the space that you can allow, you have a certain portfolio, you have a certain space. Can you allow this product to take so that much out of that space? Of course, considering the growth in market volume, because if you're successful and you have a larger market share, you also, of course, have a larger overall impact. Of course, if the market volume as such grows, so now suddenly the market is twice the size in a few years, well, the environmental space doesn't grow. So that means that the impact that's available, or the space that's available per product, is halved. So is it meaningful to talk about sustainable products? I think maybe it's more meaningful to talk about sustainable consumption patterns. So a steak, a big juicy steak, may be sustainable for you if you, for instance, do not fly as much or fly at all. You know, if you can talk about an overall sustainable consumption pattern as a pattern that stays inside the safe operating space that you have. And one product that is sustainable in your consumption pattern is not sustainable in other people's consumption pattern, perhaps. So for many products, I think this is perhaps a more fruitful way of looking at sustainability for products. And now I've been talking about the environmental dimension, but of course then there are the social and economical sustainability dimensions to consider as well at the same time. So summarizing, sustainability requires strong improvements in eco-efficiency. Remember factor 3, factor 50. Eco-efficiency is necessary, but it's not sufficient. And sometimes it's even part of the problem. When we see this rebound effect where increased efficiency drives an increase in affluence. And that's where we as engineers, I think, come to an end of our abilities. This is where political regulation needs to come in place if we want the planet to stay inside the boundaries. So industry's current focus on eco-efficiency has to be combined with this absolute perspective. It's very useful for industry to be informed not just how much better is this new generation than the old one, but also where do you need to be in 10 years, in 20 years, in 30 years in terms of your product's impact, if they should be sustainable. Because that will allow companies to find out that there are some technologies that just don't have the potential to ever get there. And they should leave these technologies, and they should focus on technologies that have the potential to become sustainable also in the long run, if they want, of course, to be able to call themselves a company that takes sustainability seriously. The normalization against these boundaries ecological boundaries, carrying capacities, allows our interpretation of the LCA results into this context. And we can say that the remaining space up to the boundary is like a scarce resource that we need to share. And we need to find ways of sharing it, and quantification of the share, the available space, and also how to allocate that remain very strong research challenges. This is something that we are working on in my group at the moment. And with that, I would like to conclude my presentation and hope that you have some questions that you would like, something you would like to discuss.
Very good, Michael. Thank you. I'll just mention to the students that if you have another commitment here in 8 minutes, feel free to duck out as needed. But if you have a question for Michael, I guess you can, we can get Cresta to take you off of mute and pose the question, or you can put it in the chat as you would like.
Or I think you can unmute yourself even.
Okay, wonderful, wonderful.
Am I unmuted right now?
Yes.
We hear you.
Does that work? Okay, awesome. My name's Tim. I had a question about, I think the way you're explaining these models and how you guys have produced them is really interesting. I was wondering, there seems to be a lot of discussion on applying these models and these expectations to developing countries, and just because, you know, we're talking about countries that have been more developed for, you know, a certain amount of time, and as a country becomes more developed, the affluence will also increase. So expectations of all the citizens and their normal standard of living is going to go up as well. I was just wondering what your thoughts are about that, and whether you think that there should be some cushion or leeway in these models for countries that are, you know, still kind of working towards creating the same standard of living that, say, we have in the United States or you guys have in Denmark.
Yes, no, this is a very good question, and this comes back to the discussion of sustainability, you know, meeting the needs of the present, because that's not just the wealthy ones. This is the need of the present generation. So that's in principle everyone. And if you think about the Sustainable Development Goals, you may be familiar with the United Nations World Goals for Sustainable Development. Talks also, one of the goals is indeed about inequality. And to get that reduced, so it's quite clear, and I think we have been on that track actually. When I was a student in the 80s, this was pretty hopeless. I mean, the poverty was just not really, you know, being reduced. If you look at the number of absolute poor, I'm not sure how much it has reduced, but the share of poor people in the world, as I said, we've doubled the population since I was born. Is really going down. So there is tremendous developments in big parts of the world. We can talk China for sure. I mean, China has made tremendous progress in this respect. Also India. India, it's predicted around 25 million people every year until 2025 are expected to move into the middle class, from being poor to the middle class. So there's a lot of things going on there, and that of course means an increased affluence. And I think the numbers I showed you were global average increases in affluence, or GDP per person in this case, and certainly these numbers need to increase. That's for sure. We can certainly debate whether in the US and in Denmark we need these numbers to increase. I think, well, as I said, I was a kid in the 60s, and I don't remember a life of suffering there. So a lot of this is not absolute poverty, but really relative poverty, that you feel poor because you don't have the ability to do what others can do. And we need to find ways of handling that, because otherwise it's a spiral. You know, it doesn't end anywhere. You know, it's kind of, okay, my neighbor has a new smart car. Why should I not have a new smart car? I have a car already. I mean, but you know, it's well, envy, I guess, is a part of human nature. But we need to find ways of handling that. But there's certainly big parts of the world where there's a big need for increased affluence, and there should be room for that. So But this is just this is part of the challenge, you know, that is in here. So the developments in the GDP per person that I showed, or the total GDPs globally, reflect this. So it's already in there that we've seen this improvement in life standard in big parts of the world. It's increased included in these increases. So it's actually into the calculation and the challenge that this then quantifies for our technology. So the more we want wealth all over the place, you know, the more efficient our technology has to be.
So can I just ask a real quick follow-up question on that? So how would you, or do you see an easy way to actually apply, like when you're looking at life cycle assessment and you go to the source of some of the resources for some of these products, is there a way to include, you know, whether those say, you know, minerals or whatever you need to produce the product is sourced from, say, a country that is using, I don't know, like slave labor, or that has a pretty substantial societal split. I guess fair trade products, is there a way to include that in the life cycle assessment instead of just the you know, environmental impact categories?
Yes, there is. There is a discipline called social life cycle assessment, because you're right that just as the life cycle perspective is very important for environmental impact in order to avoid problem shifting, it is also very important for social impacts to have the full life cycle perspective, because as a producing company, you have influence in your value chain, and you also have a responsibility to source. If you want, again, I mean, if you want to take sustainability seriously, it's not just about environment, of course. It's also, if you look at the world goals, the majority of them are about social impacts. So it's very much about that as well. Forced labor, child labor, as you mentioned, and there are tools for that. I haven't talked about it here, and I would say they are in a very early development stage. Let's put it like that. But John and one of his doctoral students led a very nice keynote about John. I guess you should share that about social aspects, social impacts of manufacturing. And in there is also a paragraph about social life cycle assessment that you can read a bit about what are the perspectives of it, what are the potentials, and also the challenges involved in it, because it's not so simple. Social life cycle assessment is difficult because, well, for many reasons, but one of them being that, you know, it's very, very local dependent. It's really about, like you say, this mining company, does it employ child labor or slave labor, or does it not? You cannot, I mean, you really need to go down to the individual company and investigate it. You can not just say because it's a mining company in Ghana, it has this or that social profile. You need really to go in and see it's about the behavior of the company towards its employees and stakeholders. Whereas the environmental, you are a bit easier off by simply assuming this is a cobalt mine, and I don't have for that specific mine data, but I do have data for 3 other mines, and it's probably similar. But you know, child labor, slave labor, that can be an on-off thing, right? So it's difficult. But it's an important perspective, and I would say it's probably today more promising in a more qualitative level. I mean, more like raising flags and say, hey, here's something to be aware of. Take care here.
I struggled phrasing that question. That was a great answer. Thank you so much.
Sure.
We have time for maybe, and again, if someone has another commitment, please feel free to leave. But we have time for a couple more questions before Michael has to go eat dinner or go have
That's okay. The evening is still young here. And not going anywhere. Everything is closed down because of Corona. So.
Anyone else? Great opportunity to talk to one of the world's leading experts on this.
Sure, I had a question. My name is Paul. Showed a graph that had these different wedges, and some were still green, and some were really red, and some were yellow.
Yeah.
To what extent can you balance loads across that those sectors? Is there any transference or ability to do that in some way where you have interactions between sectors?
That's a very good question, and because you can say that what I showed, this was you know, with the planetary boundaries, and the idea there is, I think, that as long as you are inside the boundary, you can trade off freely between these impacts, as well as between the environmental impact that we see here and social impacts that we discussed just before, and even economic impacts. So as long as you're inside these boundaries, but the notion here is that this threshold, or the boundary, which is the lower bound of the uncertainty range around the threshold, is something we need to take seriously. Because if we pass, it's not like if we pass it, you saw that several of them are red, we have passed them. So it's not like if we pass them, we're doomed. But these are tipping points, which mean that you run the risk of starting, you know, feedback loops. That means you cannot come back where you were. And all of these processes that were shown in this wedge diagram were about the climate stability. So it's not just about greenhouse gases. We affect the climate stability in many other ways. And these processes were intended to represent these other ways. And that means that if you have exceeded a boundary there, you need to concentrate on getting that back in, because you are really outside the safe operating space here. As long as you are in the green, you are inside the space operating space and a safe operating space, and you can in principle trade off freely, as we're used to in life cycle assessment. I mean, the relative form that I presented briefly, we have all these many different environmental impacts, and there we can do, through weighting schemes, we can go in and say, okay, it's worse in climate change, but then it's better in acidification, and with the weighting I have, then overall it's a preferable solution. That's a free trade-off, which we typically assume there. But this absolute perspective says that, well, there are some limits, and we need to respect these limits. So as long as we don't do that, there's no trading off. Did that answer your question?
Yeah, that's good. That's clear. So really, to follow up on that, and reversibility becomes a big deal here in terms of control.
No, you're right.
You know, if you get into a positive feedback spiral, then we've really got trouble.
Yeah, and some of these indicators are, of course, very crude. When we're talking about genetic diversity, you know, we are losing species at a very high rate. They're talking about that we are in or entering the 6th mass extinction. The 5th one was back when the dinosaurs, 65 million years ago or whenever, when they became eradicated. And you saw in that period, I mean, in, I don't know, 1 or 2 million of years, 2/3 of all species on the planet disappeared, were lost. I mean, you can see that in the geological remains from then. And they're talking about that these rates of extinction that we're seeing now is indeed a 6th mass extinction. Of course, we're just in the beginning of it, because it's not now. It's been over the last 100 or 150 years, actually, with the big deforestation we've seen across the planet. But the rates are much higher. So it'll not take us 1 million years to eradicate 1/3 or 2/3 of the species on the planet. It'll be quite quick. You know, in some centuries we'll do it. So it's not from one day to the other, but it just, the red color just means this is alarming. I mean, we really need to address this. We need to find other ways of meeting our needs if we want to avoid, you know, losing species that eventually are important for the climate stability, because most of the species we lose are not. So you have a distinction between genetic biodiversity, species loss, and functional biodiversity. Functional biodiversity meaning that, well, this function is important, and if this function is not taken by certain species, then the ecosystem collapses or changes function. But if this species is lost, maybe another species can take over. And this is what's really interesting, actually. It's not so much the genetic biodiversity, if we're talking about this regulation, it's more the functional diversity, and we don't really know how to handle that. So the problem is basically, we can lose a species and we don't know if it's important or not. And most of them, there'll be others taking over their niche, but some of them not. And we simply don't understand these processes well enough to be sure that the species we're losing are not crucial. So this is actually the tricky part about it.
Before too many more students leave, I want to have us all thank Michael. Good job, Michael.
Thank you.
I think if we can impose on Michael, maybe time for one or two more questions if there are any.
Yeah, I have one question.
Yes,
Okay,
please.
go ahead.
So, from what I see from this overall presentation is that LCA is kind of a relative way to measure sustainability. Is that right? And I, that, as you said, is like an absolute way to quantify sustainability. Am I getting it right?
Yes, you can say as a starting point, you need to take a systems perspective, which is what LCA does. So you need to look, if you want to talk about sustainability around a technology, you need to take a life cycle perspective, because otherwise you run the risk of doing problem shifting, that you improve a certain part of it and then you inadvertently create problems somewhere else that you don't know of because you didn't take the mining activities in, for instance, when you changed the design of your product and started using some new metals maybe or whatever. So you need to have this life cycle perspective, and you also need to have the broad coverage of impacts. These are the two main characteristics of LCA. That you have the whole life cycle, all the processes that are needed for this technology or product to run through its life cycle, and you have all the relevant environmental impacts covered. So you're not just looking at climate change, because you can do problem shifting between environmental impacts as well when you reduce climate change, but then inadvertently you create some other problem because you use some chemicals or you use extra land, so you have land system changes, which has consequences for the biodiversity. So these are two characteristics of LCA, and therefore LCA is needed for environmental sustainability assessment, but it's a relative view. You're right at that. And that's the problem, I think, and that's why we have suggested, how can we introduce an absolute perspective? So we have the qualities that LCA has for sustainability assessment, and we kind of address one of the weaknesses.
We had another question from, thank you.
Thank you.
We had a question from Miriam Stevens, and I'll just read it. It's in the chat. Hi, Dr. Hauschild. My question is related to what you were saying about thinking more about sustainable consumption rather than sustainable products. And I guess it also relates to Tim's question about varying levels of affluence that need to be factored into the IPAD equation. So here comes the question. Do you think it is necessary, useful, and or even possible to identify absolute levels of affluence that would allow us to achieve absolute environmental targets? Maybe being in Denmark is a good place. Scandinavia is a good place to be asking about this question.
Yeah, maybe. I think it's quite clear. I mean, my example with the rebound effect, I think illustrates very well. You can say, okay, so if we have an increased affluence as a consequence of increased consumption as a consequence of an increased eco-efficiency, then what can we do? Should we reduce the eco-efficiency to reach sustainability? And of course, I mean, that's not meaningful. No, we need, of course, to work. That's what we also can do as engineers, to work on increasing the eco-efficiency. And we've done fantastic, or our predecessors have done fantastic examples in this, or examples on how to do this. But I think it raises the point that there are some things that lie outside what we can do as engineers. We cannot design, well, only to a limited extent at least, design products that counter this explosion of consumption. Let me give you one example of if we're talking about IT, streaming, right? When I started my academic career, I think I received, this is back in the 80s, right? And I think I received somewhere between, let's say, 1 or 2 and 8 letters per week. Today, I don't receive, I receive maybe 1 letter per week, but I receive 200 emails per day. Now, the carbon footprint of 1 letter in Denmark is around 140 grams of CO2 equivalents for a letter, for printing the paper or whatever, bring it out, the whole system, the letter, 140 grams of CO2 equivalent. For 1 email, I've seen numbers that say it's around 2, 3, 4 grams. So it's extremely much eco-efficient to send an email than to send a letter. But it's extremely much more eco-efficient to send 1 to 8 letters per week than 200 mails per day. even in spite of this much higher eco-efficiency. And this is where we need to, we can say, well, but we need somehow to discuss what are the needs that we can expect to meet or expect to have met inside a society that, if we want to take this seriously, if we want to say climate change is an issue, we need to address it. Then we need to avoid that every time we improve a technology, the use of it explodes. When we were listening to LPs, you would go in, you would put it on your stereo, and you would listen for 15 minutes, and then it was over, and then maybe you'd go in and you'd turn it and you'd listen again. And of course, listening to one tune is extremely much more efficient in streaming than using an old stereo hi-fi. But we don't listen to one tune. My sons, they listen, well, not 24/7, but all the woken hours, right? So it's the same again, streaming, film, what have you. I mean, it's more efficient to stream a movie over Netflix than to take your car, drive to the cinema and watch it. But you don't go to the cinema 3 times per day, right? So this is the explosion, if you like, of consumption that is followed by the efficiency improvements that we do. So per service, we get much, much better. But then if the consumption, the number of services that we need to have fulfilled is exploding. Yeah, exactly. And I think we need to address this. In order to ever become sustainable, we need to address, and this comes back to your question about the affluence, because you could start from the bottom of the needs hierarchy and say, well, we certainly need, of course, the nutrition. I mean, that we need food, we need water. We can discuss what kind of food. I mean, how we can obtain the dietary requirements that we have, and then we need somewhere in there. I mean, somehow to get it done. I don't like the thought of it even coming from a socialist country like Denmark. I think we're called over there. We're certainly not. But anyway, the idea of somebody top down deciding this is your need. And this is why I'm talking about sustainable consumption patterns. A way of doing this could also be to have to have carbon taxes or environmental impact taxes on the products that can say, okay, but you pay for the environmental impact you cause. And the more close we are to the threshold, the higher that tax will become. That's a way of having the market regulated. So you internalize these, you don't have a carbon budget that you have to stay inside. You simply have to pay a certain amount. And this, of course, will allow wealthy people to consume more, but they do that anyway. But and then if you want to have this imbalance effect counted, then you need to do some transfers of I mean, we have that already with pensions and what have you. You can do some things like that. That could be a way of achieving it. So it's up to you what you want to use. And then you come back to what I said. It's not meaningful to talk about sustainable products, but to talk about sustainable consumption patterns. And if you think it's fantastic to have this great steak or to have this plane, this flight, whatever, and you're willing to give up other things because you have to, because it costs you now this much because there's a carbon tax on it. So this could be ways of addressing it, but we need to address this needs level because otherwise we're not going to get there.
A couple other questions, Michael. One is from Sharon Hughes, and it asks about biofuels, and what are your thoughts in general about that? Biofuels?
Yeah, well, it's tricky. I mean, biofuels is a good thing. The problem is if we want to turn, or it can be a good thing, if we want to turn our current use of fossil fuels over to biofuels, then we are talking about we're talking about an expansion in the need for biomaterials, for biofuels, which will have dramatic consequences in terms of land use, in terms of water use, and in that sense on biodiversity, because we are going to have to clear big natural lands, turn them into energy forests or energy crops. So I think in the end it's a blind alley. I think we need to use our biomass very wisely. I think what might be the big thing in Denmark right now is something we call power to X. So Denmark is, as you may know, basing a lot of its electricity system on wind turbines. We have big ocean wind farms, and we're going to erect a lot of these. So we have an overcapacity. That's the idea. and then through hydrolysis of water, produce hydrogen that you can then turn into different fuels. So you can have methanol, for instance, from hydrogen, or ammonia, whatever, that you can use for fuels. And I think this is a more promising route actually than biofuels. I mean, biofuels simply, we have been used to doing that, but the problem is its requirements on land, which is what we don't have. When you see this big impacts on biosphere integrity at the moment, it is mainly caused by our appropriation of land, where there used to be ecosystems and they're no longer there, and that's why species disappear mainly. So I don't really see, a long-term big role of biofuels. You can certainly, if you can find some biomass out there that's not used, it's just lying there, by all means pick it up and use it. But that's quickly going to end. I mean, if we want to convert our dependence on fossil fuels into a dependence on biofuels, then there's simply not land enough, and not even ocean space enough, I guess.
Here's one from Kelly Frost. Thank you, Michael. And she asked about kind of the regionalization of the planetary boundaries, kind of the ecosystem boundaries that you and I have discussed. So you want to talk a little bit about that, because, while CO2 may be a global issue, other issues are more regional or local.
Yeah. No, that's true. And this is, in my view, one of the weaknesses of the planetary boundaries framework, the way they formulated it. That's also something I know they're working on at the moment, because you're completely right that if you're looking at the impacts that were covered by the planetary boundaries, it's actually only climate change and ozone depletion that are truly global, in the sense that it doesn't matter where you emit, the impact is the same. If we're talking about the biogeochemical flows, phosphorus and nitrogen, this is very regional, or maybe sometimes even local, to what extent it's a problem to emit phosphorus or nitrogen. What's the sensitivity of the local receiving environment? This is something that we work a lot with in life cycle impact assessment. And it's a tricky point. So it's part of our research at this moment, because you can say, I presented you with normalization references that were global, that we have developed. And that's assuming a global situation. But if you think of water use, that is you can just think inside the States. I mean, in California, water is a very big issue. In Michigan, I don't think it's a big issue, not knowing the situation. But I mean, so there's a huge variation. Even within a state, you can have, from one watershed to the other, you can have a very big variation. And that means that when you want to normalize with what is a sustainable water use per person, you can define that in the US across, but you need to start transporting water all across the US in order to actually have an equal access to water. And this means that it's difficult actually to do it in the normalization as we suggest here, if you want to get into the details of it. Because at this point, you have aggregated all the different water flows, all the different emission flows, you have aggregated them into one sum, and you're not anymore able to take, into account that the sensitivity, the person equivalent, if you like, depends on where you are. And that moves it, now it becomes a bit technical, but then moves it backwards in the impact assessment of life cycle assessment to what we call the characterization level. So it's really not a normalization, but it's more something that you develop into characterization factors. And there's some of our research is about that. But this is really work in progress. I think what you can take away from this is just that we need an absolute perspective, because otherwise we're ignorant of the fact, how far are we actually, and these technologies, can they ever get us there? And then exactly how we can operationalize that absolute perspective is certainly, as I mentioned in my last slide, it's still, a big research challenge.
All right. Thank you, Michael. Wonderful job. Great. Very good. Very good.
Thank you, John.
Let's thank Michael one last time. And Michael, we'll talk to you soon. Be safe.
Yeah,
and,
you too.
All the students, be careful out there.
Yeah.
Bye-bye.
Take care.
Thank you.
Bye.